Have you ever wondered why your car gets so hot when you do things like this? It's not just friction from the pistons in the engine, it's actually a phenomenon called viscous dissipation, which is one of the most important heat sources in fluid dynamics.
We're going to walk you through one of those powerful equations in all of engineering, the general equation of heat transfer. This equation describes exactly how temperature changes inside a moving fluid, whether that fluid is air rushing over a wing or coolant flowing through an engine.
Think about your car engine. Coolant fluid flows through the engine block, carrying heat away from the hot metal. But the fluid itself is also moving, and that movement generates its own heat through internal friction. The fluid gains heat from conduction through the hot metal, but then it also generates even more heat because it's a thick, viscous fluid that resists flowing. Our equation tracks all of this.
Here's the big picture this equation answers. If I have a fluid moving through space, how does the temperature at every point inside that fluid change over time? The left side of the equation is the heat gain. First is the rho, which is the density of the fluid. This essentially means how much mass is packed into each cubic meter. For example, a denser fluid like water will take more energy to heat up than air. T is the temperature, which is in Kelvin for this equation. The higher the temperature, the more thermal energy is already in the fluid. S is the specific entropy. This one's a bit more advanced, but think of it as a measure of how disordered or chaotic the thermal energy is within the fluid. Finally, ds over dt is the derivative of the entropy. It's asking, how fast is the entropy moving in a parcel of fluid as it travels through space and time? This is a special kind of derivative because it follows the fluid as it moves, rather than looking at it in a fixed point in space. We've already seen regular derivatives in Calc AB, where d over dt means how fast this is moving and changing in respect to time. However, the material derivative ds over dt does the same thing, but it accounts for the fact that the fluid itself is moving, so what we're tracking is constantly in a new location. Putting it all together, this side of the equation is essentially just the rate at which thermal energy is accumulating inside a moving parcel of fluid. This is what the right-hand side must equal, as we're going to go into later, because this is all the sources of that heat change.
The first term on the right side of the equation represents thermal conduction. The term is nabla times kappa times nabla T. While thermal conduction may sound like a complex topic, it is actually very understandable. It essentially demonstrates how heat naturally flows from hot regions to cold regions. This is a fundamental concept in real life, like when ice melts in a warmer hand. But how would we write this mathematically? Well, first, K represents kappa, or thermal conductivity, which is a property of the material that measures how well it conducts heat. For example, copper has a very high K, or is a great conductor. This is why copper is typically used in cooking containers that heat food. Air, on the other hand, has a very low K, and is thus a poor conductor. The unit for this variable is watts per meter Kelvin. Nabla T is essentially the gradient of temperature, which is a vector that points in the direction of the greatest temperature increase. In subjects like physics, we are familiar with two-dimension vectors, but this equation's vector is in 3 dimensions. If one side of the fluid is hotter, then nabla T will point towards that hot region. The magnitude of nabla T increases with sharper temperature differences between regions. Nabla times kappa times nabla T, or the term as a whole, is the divergence of the heat flux. This measures whether heat is being gained or lost at a certain point, and how much heat is transferred. If the point is surrounded by hotter fluids on all sides, then heat will flow in, and thus this term is positive. However, if it's surrounded by cooler fluid, then heat flows out, and so the term would be negative. In one dimension, this complete term would simply be K times the second partial derivative of T, or temperature, over the second partial derivative of X, or position in a spatial distance, which you could recognize as the classic heat equation seen below. Our full equation extends this to 3 dimensions and adds the effects of the fluid's motion.
The next term is what makes this general heat transfer equation so much more complicated than the simple heat equation: viscous dissipation. When a thick fluid like engine oil, honey, or even air at high speeds is forced to flow, the layers of that fluid rub against each other internally. This friction converts kinetic energy directly into thermal energy. The first term, mu, is the dynamic viscosity, or how thick or resistant the flow of the fluid is. For example, honey has high mu, water has low mu, and air has a very, very, very low mu. The next expression in this term measures how the velocity of the fluid is changing across different dimensions in 3 dimensions. More specifically, it shows how fluid layers are shearing past each other. When adjacent layers of the fluid have different velocities, they rub together and generate heat, just like how your hands rubbing together in opposite directions does so as well. The partial derivatives, del Vi over del Xj and del Vj over del Xi, are asking how fast the fluid's velocity in the I direction is changing as you move in the j direction, and vice versa. The next term in this expression is the Kronecker delta. It equals 1 when I equals j and 0 otherwise. Thus, this term accounts for the compression or expansion of the fluid itself. The whole expression is squared, which is critical since it ensures that this term is always positive, since viscous dissipation always generates heat, whether the fluid is shearing one way or the other. And you can't really ungenerate heat. Together, the product of the mu expression and the second expression represents how much heat in total is generated by the fluid through shearing.
The final term on the right for viscous dissipation is the bulk viscosity, a second viscosity coefficient that captures heat generated when the fluid is compressed or expanded, as opposed to shearing. Zeta is a variable to show how much the fluid resists compression or expansion and how the volume changes. Nabla times V is the divergence of the velocity field. Just like how nabla T was the gradient of temperature, nabla V is the divergence of the velocity vector, showing whether fluid is expanding, which would yield a positive nabla V, or compressing, which would be negative. A nabla V value of 0 indicates no volume changes for the fluid. So, the term as a whole represents the total heat generated from fluid compression or expansion.
Together, these two viscous dissipation terms explain why supersonic aircraft wings get so hot, not just from air conduction, but from the air being violently sheared and compressed.
So why should you care about this equation? That's music to my ears. Every engineer designing a jet engine, a car radiator, or a GPU cooling system is directly or indirectly using this equation. If you can't accurately model heat in a moving fluid, components overheat and fail. The thermal design of a modern processor involves solving versions of this equation millions of times computationally. Atmospheric models that predict weather and climate use forms of this equation to track how heat moves through moving air masses. The accuracy of a 10-day weather forecast depends on correctly modeling thermal conduction and viscous dissipation in the atmosphere.
The next time you feel a hot blast of air out of an exhaust pipe, or watch a rocket launch on TV, you'll know, underneath of all of that, there's a differential equation modeling every degree.
Thanks for watching.